Boolean algebra is the mathematical language that simplifies complex digital logic into manageable expressions. Think of it as the backbone of digital circuit design. Every digital system you interact with, from computers to smartphones, relies on truth tables and theorems from Boolean algebra. It all began with the work of George Boole, who developed symbolic logic in the 1800s. Today, those foundations drive everything digital in our world. Boolean algebra was named after George Boole in the mid-1800s. Unlike regular math, it deals only with two possible values, one for true and 0 for false. In Boolean algebra, variables can only take on these two values. The main operations are AND, which is shown with a dot, OR, represented by a plus sign, and NOT, indicated by an apostrophe or a bar. All digital logic, from the simplest circuits to modern computers, is built from these basic operations. In Boolean algebra, there's a specific order to perform operations, similar to the rules of precedence in arithmetic. First, you carry out NOT operations, then AND, and finally OR. For example, consider the expression x times y plus z. You must evaluate x and y first, then take the result ORed with the complement of z. Whenever there's any doubt, use parentheses to group operations, both in written expressions and when designing circuits. This clear ordering helps prevent errors and miswiring in actual digital designs. Truth tables are a powerful tool for visualizing logic. They show all possible combinations of inputs and the corresponding outputs. For two variables, an AND gate will output 1 only if both inputs are 1. An OR gate outputs 1 if at least one input is 1. The NOT operation simply flips the value, 0 becomes 1, and 1 becomes 0. For three variables, like x, y, and z, there are 8 possible input combinations. Truth tables are essential for designing and simplifying circuits, as they make it easy to see exactly how an expression behaves. Boolean switching algebra is governed by several fundamental axioms. Closure means that any Boolean operation will always result in either 0 or 1. The identity law shows that x plus 0 equals x, and x and 1 also equals x. Complement laws say that x or its complement equals 1, and x and its complement equals 0. The commutative laws state that the order of variables doesn't affect the result, x plus y is the same as y plus x, and similarly for AND operations. The distributive law tells us that x and y plus z is equal to xy plus xz. These basic rules guarantee consistent behavior in digital logic. There are several important laws and theorems in Boolean algebra that help with simplification. The idempotent law says that x plus x equals x and x also equals x. De Morgan's laws are crucial. The complement of x plus y is the same as x complement and y complement, and the complement of x and y equals x complement or y complement. The absorption law shows that x plus x and y simplifies to x. The boundedness laws set limits. X plus 1 is always 1, and x and 0 is always 0. The consensus theorem helps eliminate redundant terms, such as in the expression xy plus xz plus yz, which simplifies to xy plus xz. Lastly, the duality principle says you can swap AND with OR and 0 with 1 to create a dual expression. The Shannon expansion theorem allows any Boolean function to be expanded concerning a particular variable. Formally, f equals x and f when x is 1, plus x complement and f when x is 0. This technique is critical for breaking down complicated logic functions into smaller, more manageable subcircuits. It's also the foundation for implementing logic with multiplexers, giving designers a universal tool to generate any digital logic function they need. Logic circuits rely on Boolean algebra to function. All logic gates, such as AND, OR, NOT, NAND, NOR, and XOR, perform specific Boolean operations. Combinational circuits, like adders and multiplexers, can be described by Boolean expressions. Sequential circuits, including flip-flops and registers, depend on switching algebra for their operations over time. Optimizing Boolean expressions isn't just about theory, it saves hardware, reduces power consumption, and boosts speed in digital devices. Even small optimizations add up, especially in devices with millions of gates. Here's a summary of the core rules to keep in mind. X plus 0 equals x, and x and 1 equals x. X plus 1 is always 1, while x and 0 is always 0. The complement laws mean x plus x complement is 1 and x complement is 0. Use De Morgan's laws to handle inversions over an and OR. The consensus and absorption laws help shorten complex expressions. Practice these rules and consult helpful resources like All About Circuits or Geeks for more examples and problem-solving techniques. Boolean algebra is the foundation of digital logic. Mastering its principles is the key to understanding how computers process information, what we call thinking. Every microchip in your devices uses these rules, millions of times each second. By learning how to use truth tables, theorems, and simplification techniques, you're unlocking the potential to design and optimize digital hardware. Boolean algebra is used for designing digital circuits, like processors, memory, and search engines. It was invented by George Boole in the mid-1800s. It's important because it's the basis of all digital hardware and algorithms. Although it might seem abstract at first, with practice, it becomes intuitive. The best way to improve is by solving simplification problems and creating your own truth tables.